So we defined group homomorphism and isomorphism and gave lots of examples. A homomorphism f from a group G to a group H is a function from G to H that respects the group operation. So f of AB is f of A times f of B for all AB in G. And a homomorphism that is also a bijection is called an isomorphism. And you write G isomorphic to H. That's how you read this underlined part if there is isomorphism from G to H. And the point I was trying to make last time is that isomorphic groups have same group theoretic properties. So if you ask the question, when are two groups basically the same? Turns out that asking whether the sets are the same is not really the right question. What you should really be asking is whether they're isomorphic. And then they're going to have exactly the same group theoretic properties. Like if one is abelian, the other will be abelian. If one is cyclic, the other will be cyclic. If one has an element of order 7, the second one will also have an element of order 7 and vice versa. So, and if you have seen vector spaces before, you might have encountered this same phenomenon as well. It's actually true for any algebraic structure. So like if you consider the vector space of all column vectors of length 4, or you consider the vector space of all row vectors of length 4, just with real entries, let's say, or the set of all 2 by 2 real matrices, or all linear transformations from R2 to R2. These are different vector spaces, so these are 4 different vector spaces. A column vector is not a row vector is not a matrix, etc. But these are all isomorphic vector spaces, so they have same vector space properties. For example, all of them have a dimension 4. If you give me a subspace, if one has a subspace of certain kind, the other one also has a subspace of the same kind, etc., etc. So the question whether these two vector spaces are the same is sort of an irrelevant question. The important question is whether they're isomorphic or not. And the same goes for groups. Okay. That's sort of the general remark I had left over from last time. Now let's start proving basic properties of homomorphisms. So the first lemma on the left down here says that if you have a homomorphism, then the identity goes to identity. And if you take inverse of an object and apply f to it, what you get is same as if you applied f to the object and then took inverse. F of A inverse is f of A inverse of that. So let me just, for convenience, write x as f of Eg. Just notational convenience. So this is an element of H. Then if you calculate f of Eg times Eg, on one hand, this is f of Eg times f of Eg, because f is a homomorphism. But on the other hand, it's f of Eg because the identity times identity is identity. So this is x times x, and this is x. So x times x is x, so you could multiply by x inverse on both sides. And this gives you x, whereas this gives you identity of H. So that's part A. This is pretty straightforward. B is also very easy. Let's see. Let's multiply f of A and f of A inverse. So note f of A times f of A inverse is f of A times A inverse. Again, I should really write here that since f is a homomorphism, this is the homomorphism property, you see. F of a product is product of the f's. But A times A inverse is identity, so this is f of identity, and by part A, this is the identity of H. So what have we got? F of A times f of A inverse is identity. And now you could multiply by f of A inverse on both sides. Which is f of A inverse. And on the left, these become the identity, and identity times that is just that. Okay, so that's part B. The second lemma up here was already stated before. It was right when we defined group homomorphism. It said that when you have a homomorphism, you have a relationship between these two groups, and you can pass information back and forth. So this is an illustration of that. So if you have a group homomorphism, let me just read part B. If you give me a subgroup on the right-hand side, I could look at all the elements of G for which, when I apply F, I land inside the green part. That's called F inverse M. It's defined up here. So the statement of part B is that if M is a subgroup of H, then this thing F inverse M is a subgroup of G. Let's prove that part. Part A would be similar. That one says if you take a subgroup of G and apply F to it, then the subset of H that you get is a subgroup of H. I'll just write the definition of F inverse M again. These are all things in G for which, when you apply F to them, you land inside M. And I want to repeat this comment from before, that when I write F inverse M, I'm not assuming that F is an invertible function. There may not be any function called F inverse. It's simply a notation for this set. And writing this set down does not require me to assume that F is an invertible function. Okay, so proof of B, let's say. How do you check something is a subgroup? Well, we could just check our basic three conditions, that the identity is there. If two things are in F inverse M, then the product is also in F inverse M. And if an element is in F inverse M, then its inverse is also there. Okay, so let's start with the identity. So I want to know whether the identity is in this green part on the left. Well, how do I know something is in the green part? I have to figure out what happens when I apply F to it. Does it land in the green blob on the right? Well, when you apply identity, when you apply F to identity of G, what do you get? You get identity of H. We just proved that. And this identity of H, is it in the green part on the right? Yes, because M is a subgroup, and any subgroup contains identity. So this identity of G must be on the green blob on the left. Well, that's the argument orally, but let's write it down. What do you have to say? I say not that F of the identity is the identity which is in H, which is in M, I'm sorry, since M is a subgroup. And this equality is from the lemma on the left, because F is a homomorphism. Since F is a homomorphism, by lemma 1a, we get that the identity goes to identity, and that is in M, since M is a subgroup, and any subgroup contains the identity. So when you apply F to this guy, you get in identity, so this guy is in F inverse M. Now that's one thing. Let's take two things in F inverse M, A and B. I want to check if the product is there. Well, what does it mean to say that A and B are in F inverse M? This means that F of those guys is in the green blob on the right. Okay. So now what is F of AB? Well, it's F of A times F of B. I should again say that because F is a homomorphism. I'm being a little brief here. But F of A times F of B is in M, since both of those things are in M, and M is a subgroup, so it's closed under multiplication. Under multiplication, and F of A, F of B, these guys are in M. So what do I see? I see that F of this creature is in M, so this creature is in F inverse M. Since F of AB is in M, we find that AB is in F inverse M. And the inverse is exactly similar. Take A in F inverse M. This means F of A is in M. Now let's calculate F of A inverse. I want to show that F A inverse is also in F inverse M. So F of A inverse happens to be the inverse of FA by this part B of the lemma on the left. Lemma 1b. Right? But this is also in M, since F of A is in M. And M is closed under inversion, because it's a subgroup after all, remember? Okay. So F of A inverse is in M, so the A inverse is in pre-image of M. What did we show? Showed that this set F inverse M contains the identity. If it contains two things, then it contains their product. And if it contains a thing, then it contains the inverse. So F inverse M is a subgroup. So next time we'll define a rather important subgroup associated to a homomorphism called the kernel. Give some examples, study its properties, etc.